Yeah, because I know that I could never really do justice to the full range of people that I've worked with. I want to start with some personal reflections. And it really goes back to my parents who gave me a foundation that was quite different. I was actually born in Palo Alto in California, where my father was the first person of African descent to get a PhD in engineering from Stanford. He returned with my mother to Nigeria to work at the University of Lagos. And I grew up in what I call the most beautiful environment any kid could ever grow up in the safety and beauty of what was then the University of Lagos, a real oasis. And in that time, I remember being inspired by people such as Chike Obi, Ayodele Awojobi, whose office was next to my father. And from an early age, I became enamored by wanting to be an engineer. I show my parents here because in many ways I got many things from them. So my father, in addition to being a lecturer, would think about big things and he set up a consulting company. And if you look at most of the skyrise buildings in Lagos Island, they were designed by his company. And so I got this idea that engineers do big things. Nigerians and Africans can do big things if they come together. So I asked my father once, I said, what does it take to do these kind of projects? And he said to me, most important thing is teamwork. So I want you to keep that in mind. And so later on, when I sent to school in England, I started learning teamwork. And I have to say that my education at high school was not just academic, but it was this idea of teamwork and how you set goals to things that are important. Can you please mute Satiria Musa? Please keep quiet. Safia Musa, please keep quiet. So, in going then from what was the early stages of Silicon Valley to Nigeria, it's important to also look at the reality of Nigeria and actually see it as a source of inspiration. And so for me, I never forgot the reality of a society where people need anything in the hustle and bustle of the Nigerian context. And so as I went through England, Afia Musa, please keep quiet. Could somebody mute Safia Musa?
Yeah, he's going to mute all of them.
Okay. And so as I went through growing up in the midst of Lagos, I learned many things that served me for life. And so later on, in going through the different places where I went to school in London and in Cambridge, that memory of a society where we have basic needs stood with me. At Cambridge, especially where I got my education, I was inspired by three people. One was my advisor, who was a very humble person, but perhaps the best person in fracture mechanics at his time, a guy called John Knott, who was extremely humble, but extremely capable at taking complicated things and making them simple. I was also inspired by Alan Cottrell, who was his advisor, who was the scientific advisor to the Queen, who at the age of 70 and 80 would still go to the library every day to be a scholar. But I was most inspired by Stephen Hawking, whom I saw every day at the Graduate Center, who in spite of all his challenges, just seemed to enjoy being surrounded by students. Those three people informed many things that have shaped my own life's philosophy. Now, when I left, I went to work in the real world for McDonnell Douglas. And for a while, I was enamored by this world where I could contribute to new materials that could drive the frontiers of aerospace. And even later, when I became a faculty member at Ohio State, that effort continued as I tried to earn tenure in the American system. And later I was, of course, invited to other places. Now, when I look at the work that I thought was important at the time, it was developing high temperature structural materials for hypersonics, advanced composites, and a lot of the sort of morphine materials for advanced aerospace structures. And those works, as I look back, were exciting. And in some ways, for me at the time, I thought I was at the cutting edge. And later, some of the composites that I developed were applied not just in the aerospace industry, but they were applied in, for example, early generation Lexus vehicles, where they took some of the in situ composites developed and extended those ideas to applications where people in Japan started using those in manufacturing. But during this period, I had one challenge, and the challenge was that my mother came to me and she asked me, Wally, what difference does your work make to the lives of people? And I said, well, they're advanced aerospace materials, they're sexy materials. But she then added, what difference does it make to the lives of people, especially the lives of people back in Africa? And that changed my life in many ways because I started to think about how to relate the work that we do to the problems that we have in Africa, the problems of health, the problems of water, the problems of energy, and a lot of these problems that needed material science to address them as African challenges, and in fact, really global challenges. And so in around 1999, when I went to Princeton, I started a new group that changed its focus. And what's important was that in each one of these areas, I was lucky enough to find teams of African collaborators and Western collaborators that worked together in groups to try to develop solutions to these problems. It turns out, if you look in Africa, 22% of all deaths occurs due to cancer. By the year 2030, it's projected that that's going to be 30% of all deaths. So I became interested in problems of cancer detection and treatment. We have challenges with water purification. Many people die, especially children under the age of 5. We have challenges with sustainable buildings that are affordable to people. And we have challenges with energy. And so I took these up as efforts in our group. And interestingly enough, one of the outcomes of doing this kind of work, one of the outcomes of doing this kind of work is sometimes you make contributions that get applied in many different parts of the world. So an example of this is this LED screen. Can somebody mute Ayodeji Noiki, please? Can you mute Ayodeji Noiki, please? Can you hear me?
Yes.
Okay. And so one of the things that happened is as we started doing this work, we got lucky. So one of the ideas in terms of fabricating LEDs using pressure resulted in a patent that was licensed by Samsung and created an idea of how you design future solar cells, which I will show you. And a lot of the work we've done since this time reflects this desire to drive African materials, but also the desire to drive manufacturing. So moving on from this, we started receiving many Africans into our group from several different countries across the continent. And I also joined a team of people that helped to develop the so-called Nelson Mandela institutions, of which AUST, of course, is a part. And I still remember the very first interactions with President Obasanjo, Nasser El-Rufai, and Minister Ngozi at the time that really led to the establishment of these networks. And one of the outcomes, of course, was AUST, where I was happy to serve for 4 years of my life on the ground in Abuja. Now, as we now go from here to various places, all the way to SUNY Poly, where I am, it's interesting to see what is common. What is common to all these places is this idea that materials can drive development, not only of people, but of industry. And here in the SUNY Valley, where I am, in the Mohawk Valley, where I am, we're trying to create a new Silicon Valley. We have two major semiconductor companies, each worth about $1 billion. And we have a third that's coming in Micron, which is a $100 billion investment. And so I'm in a university similar to AUST that's trying to drive the development of this region. But in terms of science, I want to go through now a few examples of some of the things that we've tried to do to answer this question that my mother posed, which is, what difference does what you do make to the lives of people? And the first examples I'm going to give relate to the problem of cancer. So if you look at any disease cell, very often viruses will enter these cells through a process of receptor-mediated endocytosis. And so they attach specifically to specific receptors. And then the question is, can you use that receptor-mediated endocytosis process to attract drugs or nanoparticles into disease cells? And so if you know which receptors to target, then of course you can target those receptors and use them as a way of gaining entry into the cell. And with the nanoparticles, you might do enhanced imaging, or with laser interactions, you might do laser treatment. And then with drugs attached in this way, you can also kill the cells or treat the cells. And so this idea is interesting. It's also got the advantage that you can do exocytosis, where you, after 28 days or so, reject the particles into the body. So using this idea, what we have done is to design nanoparticles and drugs that target receptors that are overexpressed on the surfaces of cancer cells. So in the case of cancer in African women, they exhibit receptors that are different often from those of Caucasian women. And so by working with the hospital in Abuja, the National Hospital, we were able to identify the receptors that are most prevalent in African women. And if you target those receptors with nanoparticles, we then showed in vitro experiments that you can take those particles into the cells by endocytosis, transport them across the nucleus, and really use this as a way of loading up the cells with nanoparticles. And then, of course, once you have the nanoparticles in the cells, you can do imaging, and you can also do laser interactions in ways that give you a number of opportunities. And then these kind of systems can excrete the nanoparticles within about 30 days. You can now do those experiments on animals where you induce the tumor. So to induce a human version of breast cancer, you inject human breast cancer cells of the type that you want to induce. And then you form these xenografts, these initial stages of cancer, within about 7 to 14 days. And those grow in about a month into metastatic tumors. So you can essentially study the tumor characteristics at the accelerated life rate of a mouse. So with methods like this, one can now begin to image the tumors. You can also image the possible metastases in the kidneys, lungs, or liver. So we've done work like this, and whenever you inject the nanoparticles, what we basically show is that you enrich the MRI contrast in those mice, and you can basically show that not only do you do this with nanoparticles, but you also enrich the MRI contrast with nanorods when you inject them into the systems. And so the idea that we are now pursuing is how to really explore the transition from doing things at a lab scale or in an animal scale to really extending this to breast MRI, which is the next port of call. One can use the same idea with cancer drugs. So you can take cancer drugs such as protigozine or paclitaxel, you conjugate them to a molecular recognition unit such as LHRH, and you can target early, mid, or late stage tumors with the drugs. Because those drugs target those tissues with specificity, what you then end up is basically a situation where you reverse the growth of the tumor. So in yellow is what happens when you have no drug and the cancer tissue grows. And then in light blue or green is what happens when you target the tissue with LHRH conjugated drug, where you shrink and eliminate the tumors in about 8 days. So with methods like this, you can therefore create targeted nanoparticles that enrich imaging or targeted drugs that shrink or eliminate the tumors. And so this work was initiated at AUST with a number of folks and continued with a collaboration with Shola Odusonya, John Obayemi, and also Teresa Zenwafo and others. And it's one of the highlights of what you can do with the kind of teamwork that we're talking about. And so with these kind of methods, we can create cancer drugs, we can create targeted nanoparticles. What's also interesting is a recent development where we introduced a new method of introducing nanostructures onto biomedical implants. This method, which uses a pack cementation method to introduce nanoscale hydroxyapatite needles, accelerates the early stages of wound healing by about a factor of 1,000. What that means is that cells that would normally spread in about a week to 9 days will spread in about 30 minutes. And that accelerated integration has a big effect on the wound healing stages associated with implants. And in this particular case, we've actually extended this work where we are now combining laser microgrooving with nanostructure development into implants in the work of Precious Etinosa and Sarah Osafo in a way that has major implications for the development of titanium implants. Here I'm showing you images of some of the human trials that we have done at Alexandria University in collaboration with Mona Murray. So I want to move on and talk a little bit about the challenge of energy. And of course, the challenge is not just the challenge of energy, it's the challenge of energy, especially for people who live on less than $2 a day. And so we're motivated, of course, by the problem of lack of electricity in Africa and many parts of the world. You notice that many of the places that don't have electricity at night actually have high level of solar incidence. And so if one looks at that, that suggests that solar is a potential solution. But you also have to think about problems of energy storage. And so this map of solar incidence is also a map of possibilities. So that's motivated our work in the area of solar. We started initially with organics. We've moved more into perovskites in recent years. And we also have delved not just into solar, but also into organic light emitting devices, batteries, and supercapacitors. Today, I'm going to focus a little bit on the work we've done on FAI-based perovskite solar cells, where essentially we create these layered structures and take advantage of the high light absorbance and large diffusion distances of perovskites. With these kinds of structures, by applying pressure to the layered structures, one can increase the contacts along the interfaces in a way that enhances charge transport, and also in ways that enable us to significantly improve the efficiencies of those structures. So if you look at the power conversion efficiencies as we increase pressure, you find that we can increase the efficiencies up to about 23.4%, the power conversion efficiencies of these devices. So when you look at these kind of numbers, these are fairly attractive because silicon solar cells, the polycrystalline solar cells might have efficiencies of 20%, and those of the single crystals might be a little higher. So we are already at the level that is close to that of existing silicon solar cells. So theoretically, if you look at the Shockley-Queisser limit, the Shockley-Queisser limit suggests that it might be possible to get efficiencies as high as 32%. And so we were motivated by this to explore the use of machine learning approaches in the optimization of our processing parameters. And so what we've been doing is to take techniques from AI, machine learning, deep learning that are responsible for autonomous systems and applying them to the design of the next generation of perovskite solar cells. We're also using basically machine images of the pressure deformed structures and relating those defect configurations to the performance characteristics that we're getting. And so with those kinds of methods, we predict that you can get efficiencies as high as 29%. And we're now working with our processing methods to guide those processing methods with deep learning, machine learning kind of approaches in a way that is helping us design our next set of experiments. We're doing similar things with batteries, where we're basically playing with lithium-ion batteries with NMC cathodes, solid-state electrolytes, LLZO, lanthanum zirconate, and lithium or carbon anodes. Again, we find interesting phenomena when you apply strains and also when ions pass through. There are induced strains that are associated with those processes that give rise to incremental deformation during charging and discharging of batteries. And those insights are helping us to develop more stable LLZO batteries with improved performance characteristics. During the application of strain, we're looking at the multi-scale contacts that exist, and we're trying to understand how those result eventually in cracking, which ultimately limits the performance of these batteries in terms of their electrochemical performance. And so with approaches like this, we've been able to make systems with fairly attractive energy storage, ionic conductivity, and a low specific resistance. What we're motivated by is the idea of integrating these kind of insights to support manufacturing enterprises that are trying to scale up the application of lithium-ion batteries into gigabatteries and also batteries for EVs. Now, again, just being grounded, one of the things that motivates us is what difference does this make for the lives of people? And so we're studying the effects of access to electricity on the lives of people. And so we've taken these solar panel systems, just 2-watt panels, connected them to lanterns that have the capacity to provide about 10 hours of lighting to people who make less than $2 a day. And we've taken kerosene lanterns and retrofitted them in ways that show that these ideas are possible. And we've also done studies in village and rural communities where you actually find that the introduction of these capabilities really transform the lives of people. Now, the third thing I want to talk about is an innovation that's really started with Professor Adewoye. So Professor Adewoye, of course, is known to everybody that's been involved at AUST. And if you remember him, he could be quite different. So one day he was found going through the bushes in Ife, looking for cassava leaves. And people thought Prof was being a bit too curious. What did he want to do with cassava leaves? He knew, of course, that cassava leaves contain cyanide, and he wanted to carbonitride steels with that cyanide. And so he processed it, and he and I co-supervised Emmanuel Kwesi and Edward Ampao, who did their PhDs on carbonitriding at AUST. Now, it turns out that another Ghanaian, Dr. Tabiria Sumadu, also came to work with me on trying to do what we thought was carbonitriding. But when we actually did Raman on the surfaces, we discovered that we had made graphene. And so essentially we developed a method for making graphene from what really started with Professor Adewoye's idea of working with cassava. And the process just requires you to control in a pack the temperature at which you do the carburization process. It turns out that nitrogen doesn't play a role when you do this at carefully developed temperatures. And you actually make graphene nanorods and nanostructures in ways that you can control systematically. And so we've developed then these ideas around how you make graphene from biological precursors. And we've been able to control this on lots of structural materials that have really amazing properties. So one of the things that we find is that these materials essentially have zero friction or close to zero friction. And so when you can get this kind of level of zero friction or close to zero friction, this is an amazing property, and it's often referred to as super lubricity. And so with our method, we've been able to do this on titanium, steels, nickel alloys, all sorts of different materials. We've also been able to show that the wear rates are dramatically reduced, which basically means you have low friction materials, low wear rates, which sets you up for lots and lots of applications of structural systems that need low friction to minimize energy losses. And so where we are is really translating this kind of work into the initial stages of trying to think about manufacturing. We've also been playing with different combinations of alloys to make high entropy alloys that have truly amazing properties. And so this is sort of a new frontier in materials design, where we're in a position to now combine different types of elements in almost equiatomic proportions to make materials with unexplored compositional spaces that have remarkable properties. So this work is being guided by theoretical calculations, computational modeling and simulations, and well-defined experiments, where we take the different parameters associated with these structures, we look at the strengthening mechanisms, we then do simulations of axial deformation and various types of indentation to understand the behavior of these materials at small scales. And then we also do indentation where we observe popping phenomena and deformation, again at small scales, to understand the behavior of these materials before we make them. And then in collaboration with Mintech, we then make these materials, and then we start studying micropillars, which we deform and start looking at the dislocation structures to understand how plasticity evolves in these structures and how these dislocations interact to form forests of dislocations that control the behavior. We then do molecular dynamics simulations of those pillar structures to actually model the deformation in ways that guide materials design. And ultimately, we take all of this information and we start predicting the stress strain behavior of these structures guided by simulations in ways that enable us to then begin to match actual dislocation structures with simulated dislocation structures associated with these specific compositions. So out of this then comes predictions of the stress strain behavior in a way that allows us to capture key phenomena. And then we blend this with studies of dislocation configurations associated with the deformation. We use this to understand indentation size effects and residual stress effects in these materials. And ultimately, we're able to capture many of these phenomena in ways that give us the capacity to simulate the behavior of these systems. And then most recently, we're also looking at the recycling of scrap into high entropy alloys in a way that allows us to develop these Sankey diagrams that show the different scrap amounts that are obtainable based on machine learning models that guide the alloy development efforts. And so with efforts like this, we think that the work that we do in developing the next generation of alloys and materials can be guided by simulations, machine learning, and computational thinking, in addition, of course, to multi-scale experiments that allow us to really be part of the frontier. And if you look at the rich reserves of materials that are present in all parts of Africa, Africa actually has 30% of the world's natural resources, 30% of the world's natural resources. So the question is, can we think about how to convert these into industry? And so in that sense, we're inspired by Africa's richest man, Aliko Dangote, who has established, of course, industries around this. And this is not just material resources. If you look at energy resources, from the geothermal resources that run from Egypt to Kenya, to the hydro resources of the Congo, to the solar resources across the Sahara and the Kalahari and much of Africa. Africa has a lot of resources that we need to start thinking about converting into wealth. And this must go from what is currently artisanal mining to real industry that's informed by research, that's informed by the capabilities that are being developed across the continent in research and development, in ways that need to create at least one Dangote for each of the 54 African countries. And so in that sense, I also suggest that we need to start looking at areas of advanced manufacturing and digital manufacturing as opportunities for Africa. So in our labs, we're developing efforts in laser additive manufacturing, fusion bed additive manufacturing, and powder processing as a way of leapfrogging our way into the 21st century. And when you start doing this, then we also need to blend this with robotics. And robotics and automation is the key to making industry viable. And I'm interested in this not just for semiconductor manufacturing and different kinds of packaging. What I'm really interested in is this idea of collaborative robotics between humans and robots and exploring new frontiers. And to your top left is an image of a robotic tractor, which has been developed by a Nigerian, Kenem Banusi, who's a professor at Olin College. And that basically begins to revolutionize how we do agriculture and how we process food into packaged products in ways that create value in our own context. And so with methods like this and with spaces like AUST, my hope and dream is that we begin to push the frontiers in these areas, in logistics, in manufacturing, in construction, in a way that is assistive, in a way that enables digital processes to really transform our communities. And then we also need to do the science around the manufacturing processes. Here we're showing you cold spray processes that we're studying to determine the influence of process variables on the ability to manufacture successful parts or to repair parts that have been damaged in service. And ultimately, one of the biggest challenges that we have is that the challenge to establish an industry is the initial investment in large-scale industry. And my suggestion for that is we should start with small to medium-sized industry that are modular components, where we bring these modular components together with digital manufacturing in a way that enables us to start small and grow and scale with resources without necessarily having to have the billions of dollars that you need when you try to start big. And so with ideas like this, the other thing that I realize is you have to work with policy people. And for me, one of the interesting adventures of the last 20 or 30 years has been working on the advisory board for the UN Secretary General, who during the time that I was at AUST and after when I left, would listen to a group of scientists give advice that really informed the development of the sustainable development goals. And it was, for me, very humbling to be part of that group, advising the Secretary General in ways that contributed to some of the things that were done. And most recently, it's been really interesting working with people like Paul Kagame in Rwanda. This was just a meeting that we had with Paul Kagame in the month of December, where we basically went to him in an effort to work with them to establish a Center for Excellence in Materials, to utilize the resources, not just of their country, but also the surrounding region in driving African development. And so in conclusion, I just want to say that what I've tried to do today is to give you a personal example of how materials, in my opinion, is the key to African development. I would say not just African, but perhaps global development. And it provides much of the tools that we need within an interdisciplinary framework. But there's a need, of course, for an African manufacturing initiative to really develop our potential beyond materials, to manufacture, to address our problems in energy, water, housing, and health. And in my own humble way, what I've learned is you can't do it yourself. You have to work in teams as you go from ideas to markets and communities. This requires partnerships with business, with industry, with government and policymakers. But above all, for each one of us that is here, the real lesson that I've learned is that you listen to that inner voice within you. Because all the things you see inspire you in so many ways to solve problems that are real in our society. And it is only when we as a team, not as individuals, work together to pursue real solutions that we can use science, technology, and innovation as engines of African development. So thank you very much. I hope this has been helpful in some ways, and I'll be happy to answer any questions that you might have. Thank you.
Thank you very much, Prof, for the nice and wonderful presentations. So before we start, Prof, I needed to read your citation, but we just went on straight. So we have new people that joined AUST. Some people don't really know you. So before we go to the question and answer session, Prof, let me just quickly read the citation that I have here with me. So Prof Wole received his BSc in mechanical engineering from King's College in London in 1985 and a PhD in material science from Cambridge in 1988. He then moved to the US as a research scientist at the McDonnell Douglas Research Lab from 1988 to 1992. before joining the engineering faculty at the Ohio State University between 1992 and 1999. And between 1997 and 1998, he was a visiting Martin Luther King Associate Professor at MIT. He was a professor of mechanical engineering and aerospace engineering at Princeton University between 1999 and 2016. He also served as the president and provost of the African University of Science and Technology between 2022 and 2024. 2014. 2012 to 2014. In 2016, he moved to Worcester Polytechnic Institute as the Bernard M. Gordon Dean of Engineering before his appointment as the Senior Vice President and Provost at WPI in 2018. He was the interim president at WPI before moving to SUNY Poly to serve as the 7th president in 2023. He is the author of 5 books and more than 400 papers in peer-reviewed journals. He is a member of the US National Academy of Engineering and a fellow of the World Academy of Science, the African Academy of Science, the Nigerian Academy of Science, the Nigerian Academy of Engineering, the American Society of Mechanical Engineers, the American Institute of Medical and Biomedical Engineering, and the Material Society of Nigeria. Thank you very much, Prof, for the wonderful presentation.
Thank you. Thank you so much.
Yeah. So the floor is open for questions. Prof, they said I forgot to mention the most important honor, married with 4 children. Okay, so we have a few questions. Ben, come forward so that we can hear you. Okay.
Good afternoon, Prof. Good afternoon, everyone.
Hi.
I got 1 or 2 things from your presentation. Okay, my name is Ugochukwu Benjamin Obi. I work in AUST as a technologist assistant at ADB Laboratory. So I want to thank you for your presentation. You talked about robotics, digital processes, and automation. So my question is, how can these technologies be leveraged in solar energy generation and storage? And what are the potential benefits and challenges that this technology can actually bring into that sector?
That's a good question.
So that's my question, Prof.
So many of the processes involved in the solar cell fabrication involve the deposition of layers that can be controlled by digital tools, whether they're spray deposition or micro or nano fabrication steps. If you leverage digital manufacturing processes, what you do is you reduce the dependence on significant experience in manufacturing that you often have when you use more manual processes. So if you actually look at many manufacturing sites these days, what they now do is they use robotic logistics and robotic processing or robotically assisted stations to enhance the manufacturing processes for these green devices, right? And when they do this, those plants are much more economically viable in many of the countries in which this is done, and you reduce the dependence on the variabilities of human skill. So my own feeling is that we have a lot of people with digital skills that can be trained to program and manage these tools and we should adopt them in our own environments to make sure that the products that we make are truly world class. Because as you know, we cannot experiment on the global stage or go through a natural evolution that takes decades. So for me, this idea of using digital processes to control things in manufacturing should be part and parcel of a strategy of building true manufacturing, not just for solar energy and green devices, but perhaps as a strategy for all kinds of devices as well.
Okay, Prof. Thank you very much. Okay, for those online, Nkechi Ofiakalu, please go ahead with your question. Please introduce yourself and then ask your question.
Okay. Good day, everyone. I hope you can hear me clearly.
Yes, we can.
Okay. My name is Ofiaka Lunkechi. I am a PhD student at AUST, and I'm in the Department of Material Science and Engineering. I want to sincerely say a big thank you to Professor for, one, his versatility, and most importantly, how he connects material science to all areas of life. I'm deeply glad, and I'm happy to get to learn about the great areas he had worked on. Personally, I'm interested in energy storage and how that could be used to solve the energy crisis in Nigeria. And that is the propelling reason why I engage in studies in the area of batteries. But my question now is, Professor, is there any recommendation for young researchers who are based in Nigeria working in the area of batteries, considering the level of challenges in making battery research in Nigeria and how they can move on in their career?
Yeah, Nkechi, it's nice to meet you. My advice to you is, first of all, with your advisors, really define an important problem where you bring your own uniqueness to the field. Because as you know, this is a crowded field with lots and lots of people working. And so you need to assemble a good team of advisors, which I'm sure you have. You need to also look at the uniqueness of what you do, and in particular, also think about niche areas that are not necessarily being covered by other people. I'll give you an example. So there's a guy by the name of Yan Wang who works on lithium ion batteries, right? And the approach that he took was he started thinking about the recycling of ion batteries. And so the focus of his work was creating value out of the recycling. And then he developed ways of making new batteries out of that. So out of this, he established a company called Battery Resources. And Battery Resources raised some funds. In fact, they raised 2 rounds of funds, and they showed the viability of the research idea. And then a few people came in and raised more money for that entity. So they raised $100 million when they demonstrated the feasibility of the idea. And they have since won 2 $1 billion grants to take their idea to scale in the US. Now, I say this because it all started with this idea, why don't I work on recycling of lithium ion batteries as opposed to what everybody else works on? And today, that company is valued at over $1 billion. So what I challenge you to do is think about ways that maybe you can be inspired by what Yan Wang did and do something unique in your research that creates value that you can demonstrate. And by the way, with Hakim and the team at AUST, you have all the equipment not just to make coin cell batteries, but to make pouch cell batteries and to demonstrate the feasibility of your idea. But you need to work out as part of the thesis process how you can get the right advice and support. Take the idea of what you're working on and don't just think about pouch cell batteries, think about giga batteries, think about batteries for EVs, and think about how your work can connect to those opportunities so that maybe one day when I get to give this talk, hopefully if I'm still around 10 years from now, I can say Nkechi, has done this. So use your research not just to learn fundamental ways of thinking deeply, but also of positioning yourself to do something unique that hopefully will establish you to really build on that idea in a way that can scale. Okay, I hope that's helpful.
Okay. Yes, that's very helpful, Prof. So, in the interest of time, I can see 4 hands up. 3. So, Prof, let's take their questions. Then maybe you just answer all of them at once, and then we can
let's
round
do
up.
it. Let's do it one at a time. Otherwise, I'll forget. Please. Shola.
Okay, Dr. Shola, please go ahead with your question. So for those that don't know, Dr. Shola is also a faculty member in AUST here and
Thank you
currently
very
the DG of NASOTEM.
Thank you very much, Professor Shuboejo, and thank you for the organizers of this training. I'm pleased to have listened, and I'm an avid listener to Professor Shuboejo because he always pontificates on the next level and the next directions that we should take. In this presentation, my summary is that Prof recommended that we should look at modular technologies that we can leverage on to start the industrialization process. And he suggested that we should look at small things that we can grow to become big. Here in NASOTEM, we are already looking at some sectors of the economy, particularly the transport sector. And we are looking at rail, pipeline, road, water, and air. And we are looking at simple things that can be motivated by what Professor Adewoye did, using the rotary furnace to develop products, simple products that can be used by all sectors of the transport industry. But the issue I see, just as we latched onto welding, is the issue of certification. Is there some scheme for global certification for welding, for example, or not welding, foundry, fiberglass, and even artificial intelligence, in its application to particularly transport? Are there some global certifications for foundry practice that we can latch onto so that the products that come off these small industries will have certification schemes? The people involved will also be certified so that both the product and the people will be developed through that method. So we are looking at things like foundry and fiberglass. Do we have some certification schemes for the products of this and even the individuals that get involved in these vocational opportunities?
Shola, there are lots of places that are developing stackable certificates of different types, not just for welding, but for different manufacturing processes. And I think for different additive manufacturing processes, different robotics practices, different semiconductor manufacturing practices. Many of these are available online. And I think the real thing, though, is to connect these training practices to industries that are scaling locally, right? And it turns out that there are a lot of modules that can be built around the kind of skills that people need to enable digital manufacturing or digitally assisted manufacturing to happen. And so what's important is to scale a lot of these training modules down to modules that meet the immediate needs of industry. but can stack up into academic qualifications if there is a desire to pursue this line. And I think as we begin to track progress in some of these areas to drive manufacturing, we should be thinking about how do we process food at the farm with digital extraction and also digital packaging in a way that is done in situ at the farm. We should be thinking about how do we process minerals into ores and ores into alloys in scalable manufacturing components that are present in the regions near where those things are extracted. And when we begin to do this, what we will find is that the cost of production is low, but the value creation at those sites then improves the quality of lives for people. And you're right, we need to do it in biteable chunks in key areas that drive the economy, and not just look for international certification, but look for certification that gives us the capacity to do these things at scale with the required skills. And I think AUST is in a great position. I think your agency, NASATEM, is in a great position to take ideas like this and start really doing certification efforts that are really valuable to people both locally and globally.
Thank you so much, Prof.
You're welcome.
All right, thank you.
Who's on the iPhone?
So please, who is iPhone?
Mr. iPhone.
Okay, Yusuf Waidi. Are you there? Okay. Akinyele.
Good morning. Good morning, Prof.
Hi,
Okay.
how are you?
I'm fine, sir. This is Yusuf Waidi.
Waidi, please go ahead.
Okay. Actually, I was just first of all, thanks for the presentations, and then I congratulate you for the job well done. I'm just a curiosity about the micro pillar that I mean the group was they fabricated when they were doing this cyanide treatment. So I want to know what was the motivation behind that? Why, I mean, developing micro pillars?
You know, one of the things that we want to do is to develop understanding of plasticity
Right here.
at a small enough scale that can allow us to do in situ SEM and also subsequently in situ TEM. And so we were motivated by this desire to understand deformation in a very basic way and to be able to go from essentially single crystals to bicrystals to polycrystals. And so that's kind of what motivated us to start looking at micropillars as structures that can contain single crystals, bicrystals, and polycrystals, and give us some of the essential features of deformation that's needed to understand plasticity at multiple scales. So that's kind of the thinking. But I have to say, it's now coupling that with simulations then means that we can capture deformations and most of the representative dislocation structures in ways that begin to help us to better understand the behavior of multi-crystalline or single crystal structures. So it's provided us with tremendous insights, and that combination of modeling and experiments has put us in a place now where we are kind of developing the next generation high entropy alloys and also thinking about recycling and the impact of impurities on recycled compositions at a scale that we can also test out experimentally. So it's this ability to couple modeling and experiments and understanding that's motivated us to go down to that scale.
Okay, sir.
All right,
Thank you
Prof.
very
Thank you
much.
for that.
And then in addition to that, there is a part that you talked about having graphene on the while doing the cyanide treatment. So I want to know, because carbon is not the only element that is present. We have some other element there also. So how, I mean, I don't really get that part.
You're right. So, of course, you have carbon and nitrogen. But when you burn it up to a certain temperature, it turns out that you drive the nitrogen into the steel or whatever substrate you have, and the carbon then starts nucleating and growing graphene at certain temperatures. And so it's reaching that particular temperature range where that graphene formation happens is the key. And then the rest of it is just kinetics. So if you leave it, then you nucleate those graphene rods, and then they grow from the nanoscale to the micron scale. So it's really basic nucleation and growth and phase equilibria. If you really understand that, then it enables you to control the temperatures that you use. And it also, the graphene itself, once it forms, it's basically the weak secondary forces that give you the low friction. So it's a great example of just taking basic ideas in nucleation and growth theory and some understanding of kinetics and bringing them together in an example like this. And it's also being curious about temperature ranges. As you begin to sample those temperature ranges, you find that you go from graphite to graphene and various other structures. So once you understand those phase diagrams, you're able to do work like this. But the thing that I didn't expect was that the nitrogen would diffuse inwards in a way that is not present at all in the graphene structures.
Okay,
Do you
sir.
understand what I'm
Okay.
saying?
Thank you so much.
Yes, Prof. The explanation is clear. We understand. Okay, we need to round up in the next 5 minutes, Prof.
Sure, no
And
problem.
so I have, okay, so Akinyele, are you still there with your question?
Yes, I'm here.
All right, please go ahead, sir.
Good afternoon, everyone. And I want to appreciate Professor Wole Soyinka for the presentation. I am Dr. Akinyele, a faculty member at the Nnamdi Azikiwe University, Awka, and I also belong to a research group at the Institute of Ecology at the Obafemi Awolowo Solid Waste, Water, and Environmental Chemistry Lab. And in this research group, we have been working on developing material from solid waste for water treatment. And we have been doing this for a very long time. But the major challenge that we have is because what we are looking into is trying to develop a material that can be used every day, that is everyday use material that anybody can just pick up and use in treatment of their water in their respective homes. But the challenges we are facing is how to equipment on how to understand these materials very well. Like the graphene you talked about, we have actually synthesized graphene from carbonized material from solid waste. But to understand this material, we are having issue because there is no equipment enough to understand them very well. That is my question. Thank you, sir.
You know, I know, for example, that the lab at the AUST has tremendous capabilities in materials characterization. And so my suggestion is perhaps you talk to some of the folks at AUST on the ground to see if they can be helpful. And the other thing is through the whole Step B thing, there's been, and the World Bank investments, there are many labs across the country that have capability that you may want to also talk to. But if those fail, please feel free to send me an email and I'll be happy to see how we can be helpful.
Thank you, sir. Thank you very much, sir.
Okay, so
emission.
Prof, there's a question on the chat here. It says the
Yeah,
use
okay.
of the use of laser beam in manufacturing to be utilized for research in Nigeria. How feasible is that with using lasers?
Oh, essentially, it's a standard piece of equipment to do laser additive manufacturing or fusion bed processes. The main thing is to basically have the powders and then the method of spraying metal powders, which then basically form solid compacts. It's very feasible in Nigeria. It's really the case of making the appropriate investments in the metal spraying platforms. They're all commercially available. But I think even more important than just buying the system is to really have a clear goal of what you're trying to achieve with it, in terms of what kind of manufacturing processes are you exploring beyond just the research. So, but these are fairly standard systems that are commercially available.
Do you want to ask question? Do you have questions? Question. Okay. Okay, Prof. Thank you. Thank you. Okay, the last for the day, Mr. Emeka. Last
Good day,
question.
Prof.
Okay.
Okay, good day, Prof. This is Emeka Uwanaka, faculty member, AUST. Thank you for your presentation. My question has to do with opportunities in semiconductor manufacturing, especially the microchips aspect. So your presentation touched on a number of industries that materials are related to. So given from President Biden to the current president, the Chips and Science Act has essentially tried to onshore more foundries to the US. And that has an inverse relationship on opportunities for those from the global south to participate in that industry. And so what are there frameworks that are still existing for scientists and researchers in the semiconductor industry from Africa? Are there those you belong to, and what would you recommend? Thank you.
So there's definitely been a global reconfiguration in how the US thinks about semiconductors. Until now, there was a strong dependence on China as a primary supplier, in addition to Korea, Taiwan, and a number of countries, and including Vietnam. But what was realized, especially over the last few years, is that the excessive dependence on China basically was a risk to the United States in a number of ways. And so as a result of that, the US policy has now started to look at Africa as a potential source of expertise in semiconductor manufacturing. The country that has benefited the most in this area is Kenya. And there's a company called Semiconductors Technologies Limited that was founded by a guy called Tony Gitinji that is now producing semiconductors in Kenya and exporting them to the Far East and also the United States. So this is the beginning of something. And by the way, this was enabled by the former ambassador from the US to Kenya. And that company is now growing, it's moving into other countries. And I recommend you take a look at that company on the web. They hire and train most of the people doing semiconductor manufacturing. And they are beginning to grow in terms of their scale in a way that I think is significant. Now, for even that company, they are working with us to gain access to the semiconductor factories that are located right in the university that I'm based at, the SUNY Polytechnic Institute, because we have two major semiconductor companies on our site. And those companies are again looking to diversify their sources. So there's a role that Africa can play if we can build the human capacity that can support us playing some role in the evolving supply chain, but it needs some serious coordination. And perhaps some of the folks in the energy group who have some of those kinds of skills may want to think about what is that role and how to grow a research effort that supports the needs of industry or perhaps some aspects of the future of the semiconductor industry. So I think increasingly in the next few years, even with the new regime, I think this need for new companies and new countries supplying the global semiconductor value chain products is going to grow. And there is some opportunity for Africa and countries like Vietnam to grow in an effort to limit the exposure or the dependence of the industry on China. So if you're interested in this, I will be happy to talk to you offline because it's an area that occupies a significant fraction of my time, especially because I live and work in an environment where the growth and success of that industry is happening. But even in America, it still requires a global supply chain for this to work.
Thank you very much, Prof.
All right.
Yeah, thank you, sir. I'll chat with you offline then.
Okay.
All right. Thank you very much, Prof, for the feedback and responses. So I will just hand over to the president, let him say a few words, and then Dr. Vitalis will give us the closing remarks. But please, when we close, there'll be a good photograph outside based on instruction from my PRO. Thank you.
Yes. Unfortunately, Prof can't join us in that photograph. But maybe
Yeah, just cut and paste, you know.
maybe we can use AI and put your picture there. Yeah, we are really grateful, Prof. When I joined the university, you were just leaving to go back to the US. But I want to assure you, Prof, that all the seeds you planted in this community, and in fact, all over Africa, they are all growing. What I can take from your presentation is the saying that is really very true, that everything is materials, and materials is everything. And all your works have shown that this continent can change. I remember one of the words you used to talk about is turning brain drain to brain gain. And I believe that all the works you have done, and you are still doing, they are continuing to solve the problems of Africa in all these sectors. So I won't talk much. I believe one of your products is here. I guess everybody here is your product. One way or the other. Our current Dean of Engineering will formally give a vote of thanks. That's Dr. Vitalis.
Thank you so much, Prof, for your kind words and also for your leadership of AUST. And please know that if there's any way I can be helpful, please don't hesitate to reach out. I really appreciate the work that you're doing and the efforts to continue building AUST.
In fact, I have to stand to give the vote of thanks. I know an abridged version of Prof's citation was read, and you could see the passion. There was a program, we were supposed to actually read that citation. I was supposed to introduce him and then read that citation before the talk. But he was so passionate to get straight into the talk, and we couldn't stop him. That is the man that we see. Prof, we are so grateful that you could find time to come and talk to us about how materials development has shaped and is shaping, of course, human civilization and human development. And just to add, Prof is a passionate mentor. I'm one of his mentees, as the president just said, and many others, if not all of us here. And he's also a great leader. You know, he's quite humble. He's right up there, but down there. I remember there was a time we were having a discussion. He said he was in a meeting with Putin, and I was scared. You know, but that is the man that when he comes on campus, he won't allow you to carry his bag. You know, and we have learned and we are continuing to learn from him. Prof, thank you so much for the time and for the lecture, for the talk. And like Babungwalo said, our president, most of the seeds that you planted, they have not only germinated, but they are gradually growing. And we continue to look up to you for support. And each time we knock at your door, you open. We have some of our students that are currently with you and you're still providing advice, still reaching out. Yeah, still reaching out to us, you know, trying to find out what is happening. So we are truly grateful. And currently we have a project which we are doing. We want to embark on powering various buildings on campus using solar. And I know you were really passionate about that. I remember during our days as students, you had to bring Dr. Olubi to train us on solar energy applications. And we even embark on the project of installing the solar street lamps on campus. We are taking that a notch higher to see that we get the roofs mounted with solar panels and powering the different buildings, the different rooms on campus. So we are truly, truly grateful. Another thing which we will also disturb you on is we are trying to set up a center for artificial intelligence and emerging technologies. And you talked about robotics and the likes, machine learning and the likes. And we know that working with you, we will get this off the ground and we'll be able to achieve a lot that will trigger the development of our continent. Thank you so much for your time. And I really want to thank also Dr. David for being able to pull you. you know, I know it's not easy to get you, but he was able to pull you. Thank you so much, Dr. David Afolaya, for that. Thank you so much, Prof. We are truly grateful. And I believe that Prof deserves a standing ovation and a thunderous round of applause. So please, can we just stay free?
I'm standing.
Thank you.
Thank you so much, Prof. Thank you. Thank you.
Thank you so much, Vitalis. Thanks, everyone. It's been a real pleasure.
Thank you.
Thanks,
Thank you,
Walu, and thanks, David. Take care.
Thank you so
Yeah,
much.
thank you, Prof. Yeah, so the audience, can you please, if it is convenient for you, can you put on your camera, please, so that we can just, yeah, please, if you can put on your camera, audience, online.
Thank you, Prof.
Is that Cleon Wazuki I see before me?
Thank you, Prof. Thank you, Prof. Money is speaking. Thank you, Prof.
It's nice to see you again.
This is Dr. John Momo, Prof. If you can remember, the guy from University College London, he told us about our rivalry from King's College when we met sometimes back when I came to UST.
Yeah. Nice to see you.
And we NASDAQ. It's nice to see you again. Well done.
Thank you, Prof.
Yeah, thank you so much.
Thank you. Thank you, Prof.
Announcement to log out. Just a few announcements. At the end of the month for February, we would like you to join us again. So this webinar series, it's a monthly one. This month is the Black History Month, and we will also be doing this together with the CPDA, one of the center here at AUST. We'll be inviting the director of the center who will be speaking on African culture and all that we need to know so that we can appreciate the Black History Month. So we'd like you to join us. The last week of February, we want you to be here and to listen to what we have to say. Thank you very much for attending this meeting.
Thank you. Thank you, sir.
I don't want to